as we've seen, calculating electric fields for these various components via integration or summation over individual charges and accounting for all the angles and so forth can become extremely grungy. What I want to show you now in the next couple of lectures is an extremely powerful method for getting results that can go directly into our database of electric fields, but we can do this with much less grunge work. As you can imagine, if we're able to replace extremely difficult integrals with a simple mathematical analysis, that analysis is going to have some very powerful, deep mathematics behind it. So it's important for us to understand that deeper mathematics, to have some kind of more intuitive feel for how the electric field works and behaves. Because after all, we can't see and touch electric fields. We don't have a lot of experience with them directly. And in such situations, there are times, and this is one of them, where you can find an exact equivalence between this new physical system you want to understand, the electric field in this case, and some more familiar situation for which you already have a great amount of intuition and for which you already have a series of results. And in this particular approach, in this particular case, that corresponding equivalent system is something mechanical. So what I want to show you now is an equivalent mechanical model for the electric field. Now, it's a model, and I don't want you to think the electric field actually is this mechanical thing, but this, if you understand the mechanical model, because it is exactly mathematically equivalent to the behavior of the electric field, you will automatically understand a lot about the electric field. So to introduce this, to set this up, let's consider a particular electric field situation. And the simple situation I'm going to begin with is going to be just a point charge. And I want to visualize first the electric field from this charge. So I'm going to show you how to draw something called a field map, which is one way to do this kind of visualization. And in the field map, I'm going to have my charge, say, plus Q here in the center of my picture. And then what I do is I go around to different points in space, say this point, and at that point, I sketch the electric field vector as a vector with its base at the point where I'm measuring the electric field. So at this point, the electric field would be outward. Maybe it goes something like that. Now, and then maybe in one case, I'll just label this E, but it's the electric field I'll be sketching everywhere. So now if I go over here at an equivalent distance, but in the other direction, I know the electric field vector that I sketch should have the same length. It's just going to be pointing in a different direction. So I may continue this way, going all the way around my point charge. So you can see then the general behavior of that electric field. The next thing I might want to do is consider things at different angles. So maybe over here, again, I'm at the same distance, so I would have the same length. As I go around here, try to make these points appear to be all on the same circle, right? They're all at the same distance outward from the center. But of course, the electric field exists in other locations too. So further out, it will also be outward, but it's going to be a little bit shorter, isn't it now? So you could continue in this way and make yourself a nice little map of what the electric field is doing at any location, and this way you can convey to anybody what the basic behavior of your electric field is.